All right, so today we're doing a note-taking guide on weak bases. Just like weak acids, they require ice tables, right? They are very, very similar to weak acid calculations in terms of the difficulty, right? If you can handle the weak acid calculations that we did last week with the ice tables, this is really no more difficult. Again, they're just little tiny tweaks, okay? So we just have to worry about those little modifications. So here's the general reaction for a base. So you've got some base reacting with water. When we did weak acid equilibria, the water was acting like a base, right? When we're doing weak base equilibria, the water is now acting like an acid. So it's going to donate H+. So we get BH+ plus OH-. Okay? And so we write an equilibrium expression here. We call it KB. And so how would we write KB expression? Concentration of BH+ times the concentration of the hydroxide ion over, do we include water? No, concentration of B. Okay, so when we were doing weak acids, the water was acting like a base, right? The acid was donating a proton to the water, and it was making H3O+, right? When we're doing weak bases, the water is donating an H+ to the base. So this is acid, this is the base. This is the conjugate acid, this is the conjugate base. Okay? So just like what makes an acid weak, what makes a base weak? KB is what? Less than 1, I heard someone say it. Right? So at equilibrium, where is the equilibrium? Reactant favored or product favored? At equilibrium, do I have mostly this or do I have mostly this for a weak base? Be reactant favored, right? Reactant favored. Remember when we talked about strong bases, we said that they fully dissociate. So no ice table needed. But for a weak base, just like a weak acid, the equilibrium lies over here, which means I'm going to have to do an ice table to figure out how this concentration changes at equilibrium, to figure out what this will become at equilibrium as well. Also notice the other thing. When we do our ice table, it's going to give us a concentration of OH-. When I take negative log of OH-, is that pH? That's not pH, that's P what? That's POH. Can I convert a POH into a pH easily? Yes, what do? You just subtract it from 14, so it's one extra step, okay? One extra step over the acids. Is everybody good on the theory here? Okay, now this is literally the exact same handout from last week. I just changed some things, right? We're still going to do calculating pH from the equilibrium constant. This will be using the 5% approximation, and then going the other way around, calculating the equilibrium constant from the pH. And we're not going to use the 5% approximation. But now we just have to modify that procedure to factor in the fact that this is now a base instead of an acid. So you're going to need your handout of K values. Now, if you look at the handout that I've given you, I think I've got one handy here. Here we go. Sure. All right, our Ka values are right here. Not a lot bigger, right? Our Kb values are significantly smaller. That's just the Kb values that we're going to be dealing with. Okay, so these are the Kb values we're looking at. All right, so let's calculate the pH from Kb. So problem number 1, what is the pH of a 0.15 molar NH3 solution? What is NH3? What's the name of that? Ammonia, right. So NH3, that's our B. So when we react that with water, what's this going to become? This donates an H+, so what does it become? NH4 plus, right, ammonium ion. And what's left of this? OH minus. Okay, so pH of a 0.15 molar solution. We need to make an ice table. Are we allowed to use the 5% approximation here? Yes, because K is significantly less than 1. So 0.15 molar minus X, so we're just going to say 0.15. This is a liquid, so who cares? 0 plus X, X. 0 plus X, X. So now, just like last week, we're going to do our exact same calculation. We're going to say to ourselves, okay, 1.8 times 10 to the negative fifth is equal to X squared over 0.15, just like last week. Right? So I got, when you multiply this times 0.15 and take the square root, I get X equals 1.64 times 10 to the negative third. Okay, so if you plug that in here, this is the value of this, and it's the value of this. Now to get pH, directly based on the information I have currently, can I get pH? No. In weak acids, you had H3O+, so you just took the negative log and you were done, right? But now we don't have H3O+, we only have hydroxide. So I have to first calculate POH, right? So POH is negative log of the concentration of hydroxide. So that's negative log of X, 1.64 times 10 to the negative third. So I got 2.79. But the problem doesn't ask for the POH, the problem asks for the pH. So how do I get my pH? pH is just 14 minus 2.79. Is this going to be a number greater than 7? Hope so, right? pH of a base should be greater than 7, and it is, 11.21. Is that a reasonable pH for a base? Yes, it is. So like I said, this is literally the same stuff as we did with weak acids. The only difference now is we have to calculate a POH first and then turn that into a pH. So as long as you understood last week's stuff, then this week's stuff is really just a minor modification. I mean, I took the exact same handout from last week and just changed all the acids to bases. Plugged in base information instead of acid information. How do we feel about this problem? Feeling good? Any questions on how we did this or why we were able to do the things that we did? All right. So I've got next one for you to try. Don't I? Isn't that what I have next? Yes. So here's a problem for you to try. I will pause the recording and give you a chance to try this. Calculate the pH of a 1 molar methylamine solution. You're going to need your KB constants handout in order to do this. And just a reminder that on a test, if you ever need a KB or a Ka, I will give you a reference page with that information on it. You will not be expected to memorize that. So take a minute and try this one. See what you came up with. So methylamine, CH3NH2. Plus water. So what is this going to become?
CH3NH3.
Don't forget the charge. Plus. Right. And then what's our other product?
OH minus.
OH minus. Yes, gotta have that charge. Okay, and I looked up the KB value and I got 4.4 times 10 to the negative 4. Okay, so we can definitely use the 5% approximation. This is a weak base. So this is initially 1 molar minus X, so 1 liquid, 0 plus X, X. 0 plus x, x. So you say to yourself, okay, 4.4 times 10 to the negative 4 is equal to x squared over 1. All right, so when you take the square root, you get, I got 0.021. Did you? So that's the concentration of hydroxide, right? Can I directly take pH from that? No, I have to do what first? Right, POH. So POH is negative log of 0.021. So I got 1.68, which is a reasonable POH, right? But is that a reasonable pH? No, that's not. So to get pH, we just subtract that from 14. So I got 12.32, which is a reasonable pH for a base. How do you feel about doing that one? Thumbs up? All right. This stuff's easy, right? For kids. Or as my kids would say, for babies. Okay, now let's do an example where we are not allowed to use the 5% approximation. And it's not because we're not allowed, it's really just because we don't need to. Okay, it's just not necessary. So you measure the pH of a 0.75 molar aniline solution and get 9.23. I want KB and PKB, and then compare that to the actual value. How would I turn a KB into a PKB? What does the little p mean? Negative log, right. So take the KB and take the negative log of it. That's it. So the first thing we need before we can do anything is we need to write our dissociation equation, right? So this is aniline, which is C6H5NH2 plus H2O liquid. What are we producing? It's conjugate acid. C6H5 what?
NH3.
NH3 plus OH minus. Okay, now the pH of a 0.75 molar solution. So where does the 0.75 go? That's our initial, right? ICE 0.75 minus X, 0.75 minus X. No approximating here because we're going to get the actual value in just a second. So the pH is equal to 9.23. If pH is 9.23, is that going to help me very much in a weak base problem? No. What will help me though? The pOH. So if the pH is 9.23, what's the pOH? How would I get that? Subtract from 14, right? So you get 4.77. Do we understand how I went from pH to pOH? There's a relationship there, they add up to 14. Okay, now once I know pOH, how can I get concentration of hydroxide? What's the relationship between going from here, going backwards? Think back last week we went from H3O plus to pH and then vice versa. If I get pH, how do I get concentration? 10 to the negative, right? So concentration of hydroxide is 10 to the negative pOH. So that's 10 to the negative 4.77. So when I did that, I got 1.70 times 10 to the negative 5th. Now when I plug that back in, is that going to actually change this value? Because I can only keep 2 decimal places. This is 10 to the negative 5th, which is way out here. So it won't change this number, right? So it's still going to be 0.75. You can plug it back in, but it's not actually going to change that number within significant figures. Plug this in here, plug it in right here. Do I now have everything I need to calculate KB? Yes, I do, right? Because KB is this times this divided by this. So KB is 1.70 times 10 to the negative fifth squared divided by 0.75. So I got 3.85 times 10 to the negative 10th. And it says compared to the actual value. If you look on your table, the actual value is 3.9 times 10 to the negative 10th. So is our answer within rounding? Yes, it is. And then how would I get PKB?
Take the negative log.
Just take the negative log of the KB, right? And it is 9.41. Remember, the weaker the base is, the higher the PKB is going to be. How do we feel about doing this one?
Lovely.
Don't need to make the approximation because you know the actual value. Although, if you had made the approximation, it wouldn't change. Because when you plug the actual value in, it doesn't change your answer within decimal places that you're allowed to keep. Feeling all right about this one? You want to try one for yourself? All right, so if you look down underneath, there's one for you to try. Working from a pH to get a KB value. So in the lab, you find the pH of a 1.25 molar of an unknown base to be 12.71. Calculate KB and PKB. What is a likely identity? Try that one. Let's work backwards on this one. You've got an unknown weak base. We can identify a weak acid or a weak base by its KB or its PKB, depending on the kind of table we're looking at. So if we've got X, AQ, plus H2O, liquid, what is X going to become? XH plus, right? Plus OH minus. Okay, and it's 1.25 molar. 1.25 minus X, 1.25 minus X. 0 plus X, X, 0 plus X, X. Now we know the pH is 12.71, but that's no good to us because this is a base. So what's the POH? How do you get the POH? You just subtract it from 14, right? So 1.29. And now if we know POH, can we get hydroxide concentration?
Correct.
Yes, we can. So hydroxide concentration is just 10 to the negative POH. So that's 10 to the negative 1.29, which I got 0.051. So when you plug that back in, that in here and that in here, we're only keeping 2 decimal places here, so that would be 1.20. And so when we then do our KB calculation, KB is 0.051 squared over 1.20. So I got 2.17 times 10 to the negative third. And so PKB, I got 2.66. Now, I just made this up, like I totally made it up. If you look at the handout that I gave you to identify this base, there's really nothing on there that makes sense because I just made this up. I totally made this problem up. I didn't consult an actual data table to make it up. I just made up some numbers. So there's nothing on your handout that could be a likely identity. But on a test, I would make sure that your answer you come up with would be something within rounding. Okay. So likely identity, I don't know. How do we feel about this problem? We feeling good about this kind of problem? Working backwards, taking the pH and getting KB or PKB. All right, let's move on to percent dissociation Because if we can calculate percent dissociation for an acid, we can calculate percent dissociation for a base. Now, if it's a strong acid or a strong base, it's 100% dissociated, so you don't need to calculate percent dissociation. But if it's weak, obviously you do need to calculate this because percent dissociation is going to be some quantity less than 100, significantly less than 100. So we're going to do this the same way we did it for weak acids. We're going to say, instead of H3O plus, though, we're going to use OH minus, right, because that's the base version. OH minus at equilibrium divided by the initial concentration of the base times 100, right? This is what you have at equilibrium. This is what you began with times 100. So we're going to do this the same way that we did for the weak acids, right? The difference is for the weak acids, it's H3O plus and HA. Same concept, though. So, let me do it. Erase that. All right, let's do this one. Hydrazine. So that's N2H4. Got to write our dissociation equation. What does hydrazine become? I'll give you the N2 part. You do the rest. N2H5 what? Plus, right. Plus OH minus. If you look up the Kb value for hydrazine on your handout, it is 1.3 times 10 to the negative 6. That's the Kb. It's on the handout. Okay, so we're going to make our ice table. So this is 0.25 minus x. So we're making the 5% approximation. 0 plus x, x. 0 plus x, x. So now we say, okay, Kb is 1.3 times 10 to the negative 6. And that's equal to x squared over 0.25. So I got x equals 5.7 times 10 to the negative 4th.
Where do you find that?
Find what?
The
Kb?
1.36.
This is on the reference page. Hydrazine's Kb value.
Oh, okay.
Is it slightly different from the one that I was using?
Gotcha.
Should be. I thought I pulled it from the same handout you guys have.
Yeah, it's right. It just didn't. Okay. Yeah. It's like H2 in H2.
Oh, okay.
That threw me off.
Gotcha.
I get it now.
Okay, so if this is x, that can go back into my ice table here. So this is 5.7 times 10 to the negative 4th. And this is 5.7 times 10 to the negative 4th. Do I have everything I need to calculate percent dissociation now? Yes, I do. So percent dissociation is the concentration of hydroxide at equilibrium. So that's 5.7 times 10 to the negative 4th over what I began with, 0.25 times 100. So I got 0.23%. Is that reasonable for a weak base? Yes, it is. Especially given how small the Kb value is. If I had asked you to find pH, do you have everything you need to do pH? I mean, you calculate pOH first, right? And then calculate pH. So you use the same information to do different stuff. Right? Because you use this same value of x to calculate pOH. You also use it to calculate percent dissociation. So I could ask you to calculate both in the same problem. Right? I could say, what's the pH and what's the percent dissociation? Because you use the same ice table to do the exact same information. To get the same information to calculate two different things. How do you feel about this one? Any questions on how we obtain these values? Now, if you remember from last week, there was a second kind of percent dissociation problem we could encounter where I tell you percent dissociation and then you use that information to work backwards. We did that with weak acids and we can do it with weak bases as well. Because it's all the same stuff. It's the same thing. It's the same thing. You're doing it over and over and over. Very repetitive. That's good, right? Because if you're doing the same thing 1,000 times, it sinks in. It sinks in eventually. That's the hope. Okay, so you've got a 0.1 molar methylamine solution, and it's 6.4% dissociated. Woohoo, that's really high, right? What's KB and what's PKB? So let's go through and work backwards. So we've got methylamine, so that's CH3, NH2 plus H2O. What is this going to become?
CH3, NH3 plus.
Right. And then our other product is hydroxide. Okay, it's 0.1 molar. So 0.10 minus X. And so 0 plus X. Now we don't know the KB, that's what we're solving for. So we can't use KB to solve for X. What do we use to solve for X? The percent dissociation, right? Because percent dissociation, let's refresh our memory. Percent dissociation is concentration of hydroxide over the initial concentration of the base, right? Times 100. So if we take our percent dissociation, 6.4% is equal to hydroxide at equilibrium, well, that's just X. And we know what our initial value was, right? Now, what's the one thing you need to do before you do any arithmetic? This is a percent, what should you do? Convert it into a decimal by what? Right, if it's being multiplied by 100 here, you need to divide by 100, so don't forget, divide by 100. So you'd say 0.064 is equal to X over 0.10. All right, does everybody see how we got that? Okay, so X ends up being 0.0064, which we can then plug in back into our ice table here, and here, and here. So that ends up being 0.009. Oops, not 009, just 0.09. And this is 0.0064, 0.0064. So now I have everything I need to calculate KB. So KB is equal to 0.0064 squared over my 0.09. So I got 4.5 times 10 to the negative fourth.
Pretty close.
It's a reasonable KB. And then the PKB, take the negative log of that. That's 3.34. I didn't check it against the handout. How does that compare to the handout?
Slightly bigger.
By how much?
4.4 is KB on the handout.
Oh, okay.
Yeah, 4.1.
That's reasonable, though. If these were experimental data.
I would say
How do we feel about that kind of problem, working backwards? So you can calculate percent dissociation, or you can use percent dissociation to calculate KB. And this is exactly the same as what we did when we did weak acids, right? There's nothing different here except we would use Ka instead of KB. All right, on the back, or on the next part of the handout, wherever it ended up printing, there are two problems for you to try. All right, You have a 0.35 molar solution of a mystery weak base. You determine that 1.32% is dissociated at equilibrium. What are KB and PKB and a possible identity? And then what's the percent dissociation of ethylamine, 0.5 molar? So take a second and chew on those, and then we'll go over it. All right, let's go over these. So you're working with a mystery base. You determine that it's 1.32% dissociated, and you want to know KB and PKB. It's 0.35 molar. That's all you need to know to be able to do this problem. So let's just call it B, so it looks like our generic equation. So B plus H2O is in equilibrium with BH plus and OH minus. Okay, so it's 0.35 molar. 0.35 minus X, 0.35 minus X, 0 plus X, X, 0 plus X, X. Okay, we determined that it's 1.32% dissociated. So 1.32% is equal to X over 0.35. When I turn 1.32% to a decimal, what value is that? 0.0132, right? 0.0132 is equal to X over 0.35. So I got X equals 0.0046. Do we agree?
Yeah.
All right, let's plug this back in. Plug it in here, here, and here. So this equals 0.35. This is 0.0046. 0.0046. So now I have everything I need to calculate KB. KB is 0.0046 squared over my initial 0.35. So I got 6 times 10 to the negative 5th. Now there's one on your handout that's 6.4 times 10 to the negative 5th. I believe, isn't there? Triethylamine.
Yeah.
6.4 times 10 to the negative 5th.
I call it close enough.
I call it close enough too.
Okay.
Triethylamine. Likely identity. How would I get PKB?
Negative log.
Negative log of this is
Is
what?
it the one that's 6.4 in like trimethyl? The triethyl is 5.6.
Oh, is it trimethyl?
Yeah.
Damn it. There we go. 4.22.
I'll try it.
Questions on how we do this? Are you feeling good?
Yep.
Are you at the point where you're just so tired of ice tables because they all look exactly the same?
I'm ready for it to be done.
Good.
I'm ready for spring break.
So we got next week of buffers, and then we've got KSP, but it's all the same. It's all the same.
We have homework. Well, I know we have a quiz Friday. I was just asking them.
I can't remember if I scheduled the exam before or after spring break. I have to look at the syllabus.
Quiz is probably gonna be over.
I mean, but exam 2 is literally ice tables until you faint. I mean, that's exam 2. If you want to know what's on exam 2, it's just a zillion ice tables.
It's this right here.
But that's good, right? That's minimal studying because it's all the same thing. All right, let's focus in for one more problem. We got C2H5NH2 plus H2O. What does this become? C2H5 what? NH3 plus hydroxide. You need to look up the KB in your handout, KB is,
5.6 times 10 to the negative 4.
that's right, 5.6 times 10 to the negative 4. So set up our ice table. 0.50 minus x. Do we make the approximation here? Yes, because we can use KB to determine that. That is an appropriate way to go. Okay, so now we just say to ourselves 5.6 times 10 to the negative 4th is equal to x squared over 0.5. So I got x equals 0.017. So this is asking for percent dissociation. So percent dissociation is just x, well, these two values are the same, x, over initial times 100. So 0.017 over 0.5 times 100. So I got 3.4%. Was that reasonable?
Yes.
Questions on how we did this problem? Feeling good? Any other questions about weak bases? All right, I will stop the recording here.